Hello, Marcelo. Can you hear us? No, we cannot hear you.
Hi, this is Sergio. Yes, good morning. I can hear you very clearly.
Okay, perfect. Thank you. So I think Marcelo will start with his talk, but we cannot hear him.
Can you hear me now?
Yes, there is an echo, but we can hear you.
It's better now?
Yes.
Oh, sorry. Too much technology.
No, but it's okay now.
Unbelievable. I work with two computers and one cell phone, and
Okay, but I think it's okay. So maybe we should start. We had here with us Professor Lionel Calviani, who is the project coordinator of the FunGlass project, which is invite you to this third session of the FunGlass Days. So you will have 2 more sessions in the next 2 weeks, and I have written the address again to register in the chat in the discussion of this session. So Lionel, would you like to say one word as an introduction? Okay, so I know that he maybe has some network problems today, so maybe we should start and then you can maybe say a word to us after your talk, Marcelo, if you would like.
yes, Vanessa, can you give me the authorization to open my? It is disabled screen sharing.
So Lionel, do you have the right to give the hand to Marcelo? I would just give me 1 second. So that's okay. We can see your screen. If you want maybe to put the slide on the full screen, it will be perfect.
Yeah. It's okay?
Yes, perfect. Thank you. You have the floor.
Okay, thank you. And first of all, I'd like to thank you, Funglass, and all of you to be here today to listen a little bit about what we are doing here in Brazil. So it's as Vanessa told you, this is a consortium, an international consortium working on glass and related materials. And so this morning, I will talk a little bit about the magnetic glass. This is one of the lines of research we are doing here in Araraquara. After me, Sydney will talk about functional glass and inorganic hybrids. And then later we have two invited. So the first one will be João Batista Rosolém, that will talk about the projects using the special glass and fiber systems for photonic laboratories, part of the CISPhoton. It's another project we are partners here in Brazil. And then Francisco Smolka from Optolink will talk about development of passive components and system based on optical.
Marcelo, I think we have lost you.
United Nations. This is related to the International Year of Glass from the United Nations. So I would like to present you first our research group. So here in Araraquara, we work in two main groups, so photonic materials and LaVie. So we have two different names here. We are all the part of the photonic groups. So myself, Marcelo, Professor Sidney Ribeiro, Dr. Silvia Santagnelli, Dr. Yunus Mesadek, and more recently, Douglas Franco that joined us. So we are the photonics here in Araraquara. For those who don't know where we are, so this is the Brazilian map. We are here in the São Paulo state. So these are all the campus that Unesp has in Araraquara. Just if I can't find my pointer. So we are here almost in the middle of the state in Araraquara. So this is our campus, the Chemistry Institute. So LaVie and LAMF are here. This is the entrance. Just some nice photos of Araraquara. That's the Indian name for House of the Sun. So we have some nice pictures here. So this is the outline of my talk. So I'll talk about a little bit about magneto-optical effect, maybe mainly about the Faraday effect. So a little bit of about magneto-optical glass ceramics, magneto-optical hybrid materials, magneto-optical glass, and we'll finish with the present and future applications and acknowledgements. So when we talk about magneto-optical materials, we can find mainly these four effects. So Faraday effect, Moog, that is Kerr effect, the Cotton-Mouton effect, and Zeeman effect. Here in Araraquara, we work with materials. We are exploring the Faraday effect. So I would just talk about this one, but we can in the future also we are planning to work with other effects like this, exploring this with our physicians partner. So what is the Faraday effect? Well, the Faraday effect is defined. It's the effect defined by the rotation of an angle, theta, of a linearly polarized light beam when the light travels through an optical path of known length under application of a longitudinal magnetic field. So this is the definition that we can find on the book. For example, here, Yamane, in the book. And basically, so we have an angle, and we have three components here in this equation. The Verde constant, that it's intrinsic of the material we are studying. B is the magnetic field, and L, there is the length of our device. So how we can achieve very high sensitivity using this kind of application or materials. So first of all, we need to have a high to measure low magnetic fields. In fact, we have high sensitivity to measure the low magnetic fields. We need to increase the value of the Verde constant, or we need to increase the L component. So usually the magnetic field, if you are we are thinking about use these materials to sensor as sensors. So the magnitude of the B can change, for example, from 1 to 10 to minus 15 Tesla. So 10 Tesla, so it's a very, very low magnetic field. And to achieve this order of sensibility, we need, for example, if you work with a device, we need to increase, for example, the L. So we need kilometers of, for example, of a material, for example, an optical fiber. And also we need to work with the Verde constant. So usually we need to increase the Verde, and also we can increase the L. So this is what we are trying to do here in Brazil now. We are trying to work with these two components and to get more sensitive materials. So the most part of the glass compositions that we can find in the literature or even in the market, they present a magneto-optical effect. It can be very not so sensitive, but and some of the glass can reach a relatively high sensitivity. So to work on these properties, the sensitivity of the device depends on several properties. We can work on the glass composition, for example. So changing the glass composition, we can change, for example, the refractivity index of the material, and it is related also to the increase of the Verde constant. So we can change the composition and change the properties. We can change also the wavelength used, because the Verde constant increased a lot with the refraction index when you increase the refraction index. And how to do that? Usually when we work with on glass, we can change the composition by incorporation, for example, of paramagnetic ions that can be transition metals, for example, or rare earth. And also, in this case, we need to take care the optical absorption spectra of the ions, for example. Here I just put two examples, so dysprosium and terbium. And as we can see here, when we have a high content dysprosium sample, we have the absorptions in the infrared and the visible region. And so to work with the magneto-optical effect, we need to avoid the wavelength where we are interested to work that has some absorption, like here. So terbium is one of the most used ion to study the magneto-optical effect in glass, because it has only this low absorption here in the region of 480 nanometers, and then other absorptions in the infrared, the middle infrared. So how to choose the composition? We look to this big table here, we have all the rare earths. Why I put this? Because they have the biggest magnetical susceptibility. That is why what we are interested. So we have here for gadolinium, terbium, dysprosium, holmium, and erbium, the highest magnetical susceptibility. So this is why usually we choose terbium or gadolinium. Gadolinium is a little bit lower than terbium, and erbium and dysprosium and holmium, even in erbium also. They have lots of absorptions in the visible range. So terbium is one of the most used ion in the literature. And when you think about changes composition, this figure here can show us the Verde constant as a function of the quantity of terbium, for example, and in different families of glass. So here we have phosphates, silicates, aluminum silicates, bore germanates, and it's almost linearly. It's increased linearly. And in these families, one of the main changes, of course, we have all the composition here, but the refraction index of the matrix usually increases in the same direction here. So as reference compounds here, we have a TAG and TGG that are two crystalline materials. So terbium, gallium, garnet, and the TGG is one of the most known one. So we can find it on the market, use it in a lot of applications. So usually people work with glasses trying to reach the values of TGG. So the Verdin constant, it's limited in glass for practical purposes. It reaches a maximum value around 230 rad per Tesla per meter. This is one of the biggest Verde constant to find on the literature. So the main problem is the fact that the addition of high contents of paramagnetic ions usually make the glass unstable thermically. So it will avoid, for example, the obtention of a very large L. For example, if you intend to have optical fibers. So we must have a compromise here between the amount of hertz, the glass composition, and the thermal stability that we can reach with this glass. As an alternative, there are two possibilities. work with more stable compositions. It means lower values of Verde, but and prepare, of course, optical fibers, so we can gain a little bit more with the L values, or we can synthesize hybrid materials containing magnetic nanoparticles. The Verde constant of magnetic nanoparticles is 10 to 3 or 10 to 4 orders higher than those present in glass. The main problem is the fact that you have particles. So how to manipulate these particles, how to put them in a way to work. And of course, when you're looking for an application, the practical uses of these nanoparticles. So we started with this project that we named it Glass Project. That is a project that intends to study different approaches to obtain magneto-optical and magnetic materials, mainly concerning composed of glass. So we studied new compositions containing transition metals and rare earths for fabrication, of course, of glass and glass ceramics, and hybrid glass that are this glass compositions with magnetic nanoparticles dispersed on it. So during these last 4 years, we published some papers. We have a patent in 2019 concerning this magneto-optical glass. So when you talk about magneto-optical glass ceramics, it starts with the work with this guy. It's Peter Schultz. In 1968, it was the first magnetic glass ceramic prepared. In that time, Peter was working at Corning, United States. In 1970, he did the first patent. Here, I have the opportunity to meet Peter in a conference some years ago. So we discussed about this glass ceramics, and he sent me his PhD thesis. It was quite nice. And so thinking about to get magnetic and glass ceramics, some years ago we studied this multi-component glass system here containing lead, germanium, bismuth, gallium, and it was doped with several rare earths. In that time, we were intending to obtain white light emission, but we had some surprises concerning this glass. So you observe that when we put some rare earths, so the glass crystallizes, and it crystallizes with this kind of glass ceramic face. It's a cubic one, very nice crystals. And then when you characterize these crystals, those crystals, we got some composition. The composition is similar to those of gallium garnets. So it's a rare earth gallium garnets. Those here are some compositions that we can find in the literature. In our case here on the glass, we have the same kind of structure, a special group, and in fact, we got a gallium garnet. So the optical properties of these materials are interesting for us, but we think if we change the rare earths by terbium, is if it was possible to get the TGG, the gallium garnet crystals that will, as I told before, this is the most used one in the market, with a Verde constant in minus 134 Rad per Tesla per meter, this wavelength. And what you've got here, sorry, this is, for example, one use of a TGG is in the LIGO, the Laser Interferometer Gravitational Wave Observatory. This was one of the detectors used to get the gravitational waves from years ago. So they are using it as Faraday rotators and optical curators mainly. You can find a lot of literature about TGG and the LIGO in the website of the Caltech. So we changed the composition of our glass. We put some terbium there, and what you see here, it's the amount of crystals increasing. As a matter, we got more time to cool the glass. So these crystals, they are formed during the cooling of the glass. So if you control the quenching rate, we increase the amount of crystals inside the glass. And when we characterize this, so we got the TGG crystals, and I'm not online anymore, or I'm online. So let's see. I lost my connection. Up. I'm back. Here again. So as I was told you, I have the when we change we put terbium inside this glass, so we form the TGG. It was characterized, the crystalline structure, the magnetic properties. So now we are working on these materials now to evaluating the magneto-optical properties. Right. So the other line of research we have here, we have been working with hybrid materials. So as I told you before, the Verde constant of magnetic nanoparticles are much higher than the ions that we can put in the glass, but we need to work. We need to try to disperse these nanoparticles inside glass matrix. This is the approach we are doing here. So for this, we use polyphosphate coacervate that is a phosphate that can be transformed in glass, and it's obtained in low temperature. So we use a solution of sodium polyphosphate, and we add to this solution another solution of calcium chloride. So after one concentration here, it will form a gel that is the coacervate. There is a phase separation here. Then we dry it, and we add the nanoparticles to the coacervate, and we melted this coacervate in a furnace for some minutes to eliminate water, and then we can obtain glass with here. It's with different contents of nanoparticles. This was the first work we did, and we observed that the nanoparticles were not really well dispersed into the glass, so we could find some problems, and we decided to change the chemical route to obtain the nanoparticles. So in this work here, Julian worked with the iron, and in fact, what we did here, we protect the nanoparticle with a shell of silicate. So it was the name is stellate, like this, more or less. So when these are the nanoparticles, they are monodispersed, and then here we can show a magnetic nanoparticle here with the core with 20 nanometers, and the shell, it's this big one here with more or less 100 nanometers in diameter. So these nanoparticles were monodispersed, and then when you disperse it into the glass, so we did the same procedure as I showed you before. So we got some samples like this with the nanoparticles inside the glass, and the shell was still here. So we could identify that some silica dissolved into the matrix, but it was not so bad because in fact it stabilized the phosphate glass. So we could find here the nanoparticles inside the glass. So for with this kind of approach, so we could have a better control of size and distance between the particles. We got a homogeneous and transparent sample, and one interesting thing here is this methodology allows us to add, for example, metallic nanoparticles such as cobalt to platinum inside this glass. Otherwise, it was almost impossible to add metallic nanoparticles inside the oxide glass. So we have no other reference concern this kind of synthesis. We did that. We published this paper with cobalt platinum later. So the main arm of our research here are the magnetic optical glass. So we start this study some years ago, work on transition metals, but transition metals has some drawbacks. One of the main drawbacks is when you try to increase the concentration of the transition metals inside the glass, usually it became dark, like here with iron oxide. One of the main possibilities is to work with manganese. If you can stabilize the oxidation state of manganese in just 2+, so it presents only one small forbidden absorption band around 410 nanometers, and then we can have some glass like with an absorption curve like this. This is the yellow one here in the graph. However, when you try, for example, to thermal treat this glass, or what we were intending in this case was to put this glass in the form of optical fiber, it changed the color. So you need to protect the drawing atmosphere using argon or nitrogen to avoid the oxidation of manganese that in this case passed from manganese 2 to manganese 3. So we have here a charge transfer absorption, and the glass become very, very pink here, dark. And let me change again. So in the beginning, we work with some compositions. So we were intended using manganese. So we got this kind of samples. They are very luminescent, but the luminescence was not really what we are interested. So we try first one first approach to really see if this glass were magnetic or not. So when we approach a magnet, this is a neodymium-based magnet to the sample, so it is attracted to the magnet. So this was our first really good result. And after that, we changed the composition of the glass, we increased the amount of manganese, and then we can find glass with a much more attraction to the magnet now. So now we are studying this magneto-optical properties of these materials. When you talk about paramagnetic ions, so compared to what we can find on the literature and on the market, we have the silica optical fibers. So these are the Verde constant of the silica. For example, at 660 nanometers, the Verde constant is 2.4 Had. In 1310 nanometers is 0.5 Had per Tesla per meter. And in the telecom range here, we can find it's something around 0.589 Had per Tesla. So when you ask about why to use the higher Hertz, so as I told you before, we can use the terbium, and it shows the most promising properties to increase the value of the Verde in this kind of materials, because even if this Verde constant of silica are quite low compared to results that we find in the literature now, the silica is used for these optical components, mainly in the infrared. So in this case, we pass to compositions, work with terbium, and then they are also magnetic. So we just have here some images about some videos about this glass. These are borrow germanate glass, so we can put a high content of terbium on this composition. Of course, we need to manage it also, because terbium at high temperature and high concentration, it can change the oxidation state, passing from terbium 3+ to terbium 4+. And in this case, the glass become dark. So we lost the optical properties, but work on the chemical composition again and putting the correct agent to control this redox problem, we can get very high concentration of terbium without oxidation. So this is just some paramagnetic effect we studied in this class. So in this case, we obtain, here in this system, we got some samples. So as I told you, now we are able to control the color of this glass by put some oxidation reducing agents here. And we got for the same wavelength that the silica, we got here minus 130 Tesla, Had per Tesla per meter. That is in the same range of the TGG. So this is interesting for us. So with this composition, we work on a preform. So we prepare a preform, we draw it into fiber, and then here you can show the magneto-optical fiber. Macroscopically speaking, we can show the properties. So this is also other figures. We could obtain core shell optical fibers. So this work was done in cooperation with Professor Younes Messadek in CLPL in Canada. So this is very nice fibers. So back here to this slide. So comparing now our results with the silica fiber. So we can see here at 880 nanometers that were just here. I show here the lower attenuation of our fiber. So we got, in our case here, it's minus 2.05 Hz. And sorry, this is for silica, and for us, for our fiber here, it's minus 32.5 Hz. So we have a factor of 16 almost here, and increasing the Verdet constant at this region. And also for the telecom range here, telecom wavelength, we increase to minus 9.5 Hz per Tesla per meter as compared here to silica. So this is a very nice result. So concerning the application of these materials, we can find a lot of them on the literature based on Faraday optical isolators. For example, here, Faraday optical isolators. Some devices based mainly on Hall effect. It's not optical, magneto-optical, it's based on Hall effect, but it's, the intention here is to use our materials to substitute this kind of device. So to measure the electric current and also very low magnetic fields. This is one of the works we've done recently. It was submitted to publish in Optics and Laser Engineering the beginning of this month. So we use our fibers as a specklegram. So we use the fiber as a fiber sensor. So here we have a setup, how it was done. It was done in a cooperation with Professor Cristiano Cordeiro from Physics Institute at Unicamp here in Campinas in Brazil. So we have a laser. Here we have polarizers, and we have the coil here that makes to apply the magnetic field. And this blue line here is our fiber. In this case, it has 10 centimeters. And what it do here is to analyze the speckle. It was the light that goes out from the fiber with this webcam here. So we analyze the image of the speckle before and after to apply the magnetic field. So with this, using some equations, of course, here, we can see here the signal that when the Z intensity here decrease when we increase the magnetic field here, and then we can see on the right here we have 3 different optical fibers. In this case, it was with 6, 8, and 10 mol% of terbium. The 6 is the red one, 8 the green, and 10% of the light blue here. And we see that the sensibility, this is, we can relate Z with the sensibility. So the sensibility increase as a function of the terbium content. And the result we got here, it says for our fibers, we have 59 times more sensible than and with a resolution 6 times more important than the multimode fibers, says silica multimode fiber, and with a resolution, the maximum resolution attending 2.5 millitesla. So as I told before, here we use just 100 millimeters of fiber. So we can increase the sensibility, usually if you increase the L here. And so we are working on this right now. But why to study high sensitivity glass? So if we talk about, for example, some biomagnetic signals, we can find here, for example, MCG, magnetocardiogram, magnetoencephalogram, magnetomyogram, or magnetooculogram. So this the range of magnetic field generated by this kind of interactions are here around 10 to minus 10 to 10 to minus 14 Tesla. So these are very, very low signals. And of course, to attend this range of sensibility, we need to increase a lot the sensibility of our materials. So this is why I think one of the approach we need to study a little bit more now is concerning the addition of the magnetic nanoparticles to our materials, mainly in glass. So this is another approach we are intend to do in the future. We are studying these ribbon fibers with our colleagues in Bordeaux. So the idea here is just take one glass, a rectangular glass, and put in the form of an optical fiber. We got these fibers, and now we are intending to characterize and then to do more functionalities to them. And just closing this presentation, we need to work with new stable glass compositions with a lot of Hertz, for example, inside to increase the Verde constant, increase the optical quality of the optical fibers we obtained it because we never did something in this direction. Now we are working on the purification of these fibers and to put out the water, for example. Develop new hybrid materials containing magnetic nanoparticles that can be used as glass or thin films, and test the sensors, of course, in the real world to evaluate the potential of these materials. So I would like to acknowledge all our collaborators here in Araraquara and our funding agencies, FAPESP, Fundglass, the CERTEV, the Center for Research Technology, Vitreous Materials, CAPS and CNPq, CISPHOTON, this is the National System of Photonics Labs, you make part since last year, and also our collaborators in Bordeaux from CMCB and ESM, and also from Quebec, from CLPL. So just to say that we are hiring here in Brazil who is interesting to work on these fields. The deadline is next Friday. And thank you very much for your attention. I'm sorry for this problem here with the connection. I think you can pass for some questions. I don't know if you have enough time because I think I'm a little bit late. I think we can pass to Sydney directly, and then later, if you have some questions, we can make the questions all together.
Okay, thank you, Marcelo. So I must begin my presentation. Let me try to share my okay. I think you are all seeing my presentation, yeah?
Yes.
Okay. So thank you. I'd like to start Leonel Camignoni and Vanessa Machot for the coordination of this network. And of course, our colleagues from Portugal, Canada, Germany, and France. I hope this consortium will be the start point of a long-term collaboration between our groups. And so, and also, of course, thank you for the organization of these affiliate days celebrating the International Year of Glasses. So my name is Sidney Ribeiro. I work here in the same place as Marcelo, in the Institute of Chemistry of the São Paulo State University. And Marcelo already showed you where we are, so I will skip this slide about our state in São Paulo. And this is a picture taken 3 years ago, celebrating the International Day of Light on 16 May. So 2 weeks ago, we again celebrated the International Day of Light, but we still don't have a picture to show you. So these are the guys of our group. So I thank them very much for the hard work and all the results I will show here. These are all our collaborators. This is a list, a big list of collaborators from other universities here in Brazil and also other countries. So I thank them very much for the collaboration and also for the friendship. And of course, I'd like to thank our funding agencies here in Brazil, CAPES, CNPq, FAPESP, and of course, the FunGlass Consortium, and the Joint International Research Unit that we have between UNESCO and Université Laval in Quebec, and also the National Institutes of Photonics, which is a network, a Brazilian network of more than 40 groups, research groups, distributed all over the country, dealing with photonics. So what I will change a little bit the subject from what Marcelo showed you. I'd like to talk about sol-gel methods and organic inorganic hybrids. These are very popular methods today, and the big success is that these methods are low temperature methods. We deal with liquid precursors, so we can play with any composition, and it's a bottom-up approach. Let me introduce the pointer here. It's a bottom-up approach. I mean, we can control the size and properties of the material's building blocks, the colloidal particles, the nanoparticles that will make a macroscopic material. So when we are talking about glasses and ceramics, we deal with the classic method established 1,000 years ago. And so we mix our precursors, oxides, carbonates, nitrates, and we melt them at high temperature, and then we cast to have the temperature quenching. This is very, very classic method. we are talking about sol gel, doing the same materials at low temperatures. And I must say that these methods are not that new. These are the first papers published on that on the 19th century. So these papers deal with the liquid precursor. They establish in these papers that under acidic conditions, this precursor leads to silica in the form of a glass-like material. So this is a low temperature leading to silica. This is our famous precursors, the liquid precursors, TOs, tetraethyl orthosilicate, and TMOS, tetramethyl orthosilicate. So these are alkoxides, liquids, that we will control the hydrolysis and condensation to obtain our macroscopic materials. So the process is summarized here. We have a precursor, a molecular precursor that we hydrolyze in order to obtain colloidal particles with controlled properties and sizes, and this we call a sol. And then by removing the solvent, we can have a gel. It is a porous solid, rigid one that we can densify or not in order to obtain a dense solid. So in terms of making macroscopic materials, this is the critical step because we need to control the material in order to not to have cracks, for example. The colloidal sols are very stable. We can keep them for months. So we have a collection of nanoparticles in a liquid solution. This summarizes again. So we have our precursor, we hydrolyze them to obtain the sol. And from the sol, we can do a lot of things. We can do coatings in order to have what we call a xylogel film that we can densify. We can have, by gelling, we can have particles. From these particles, we can obtain the xylogel or the ceramics. We can precipitate in the form of uniform particles. We can spin the solution in order to have fibers. We can dry in supercritical conditions in order to have what we call the aerogels, or freeze dry in order to have the cryogels. So a lot of different materials can be obtained. By controlling the reaction conditions, I mean, the hydrolysis and condensation reactions, and we can play with the pH, the catalyst, the water to silicon molar ratio, for example, the aging time, we can obtain completely different materials. In general, if we use acid catalyzed processes, we will have linear or randomly branched polymers. Macroscopically, this will present porosity at the nanometric scale. So they present in general high optical quality. They are transparent. So we can do preforms or thin films. In the other side, if you use base catalyzed processes, you will have highly branched clusters. It means that we will have particles. In general, submicronic particles of silica. This is the so-called Stolberg processes. And this, the particles are in fact called in the literature nanoglasses. If we control the packing, for example, we can get to photonic crystals. Nature does that. So here you have opals. You must know opals. These are opals from Brazil. They are high quality opals. And they present these beautiful colors. And if you look at this material under the microscope, you will see a collection of silica spheres packed in an organized way. Since these spheres, the size of these spheres is of the order of the wavelength of the visible light, you will observe diffraction of visible light by this colloidal crystal, as we call it. So the colors you see in the opals are the black diffraction of visible light. These are very interesting materials. We can use the silica particles and modify them In this case, with these complexes here, you see here europium, and these are the organic ligands around europium. And one of these ligands is modified with an alkoxide, it's a silicon alkoxide group. This will allow us to graft these luminescent species on silica particles. So we did this, and so this material, these silica particles modified with the luminescent complex, can be used in imaging. So you see here an image of a microscopic sample excited in the infrared. So what we have here is a multiphoton imaging. We have here at right a general scheme of the energy levels concerning in this process. So you have here the energy levels from europium, the well-known transitions that lead to the red emission of europium ions. And you have here the UV energy levels of an organic ligand that is used to absorb the excitation light. This is what we call an antenna effect. So you can get to these levels either with UV lamp directly or with an infrared laser in a two-photon process, as I show schematically here. So by doing that, you can use femtosecond lasers emitting in the infrared in order to populate these ultraviolet levels and observe the visible emission of europium. So this is the excitation in blue here. You have the excitation spectrum obtained in the infrared region of the spectrum. These silica particles can also, they can be modified with lanthanides emitting in the infrared, and they can be modified also with the same kind of complexes of ruthenium. By doing that, so you have here a silica particle, ruthenium absorbs strongly in the visible. So a ruthenium will absorb visible light and will transfer the energy to the complex of the lanthanide complexes emitting in the infrared, with a lot of different applications for this material. You can have mononuclear complexes like this one, or binuclear complexes like this one. So this is a complex where you have ytterbium and ruthenium. And in this case also, you can have the excitation in the visible and the emission in the infrared. Silica can also be used to coat magnetic particles. Marcelo just showed us some examples. So in this case, we used iron oxide, we coated with silica, and then we modified the surface with the luminescent compounds. So what you see here is a cuvette with the particle suspension illuminated in UV. So the red color you see here is the luminescence of the particles. And we have a magnet outside the cuvette here, just to show that the particles are magnetic. So this is a multifunctional magnetoluminescent nanoparticles. You can play also with upconversion nanoparticles. I will come to this slide in a minute. Upconversion nanoparticles are particles made, for example, with ytterbium and erbium lanthanides. You have here the energy levels of the ytterbium and erbium. When you excite in the infrared at 980 nanometers, ytterbium will absorb the photons and will transfer to erbium in a successive way, addition of photons, populating high energy levels. So what you see here is that by exciting in the infrared, you observe emission from erbium in the red and in the green. In the green, you have two transitions from two levels to close levels. So this is very interesting because the population of these levels, therefore the intensity of these two green lines, depends on the temperature. So the population, the relative population of these two levels obey a Boltzmann expression like this one. So by playing with the relative intensities of these two green lines, you can have information about temperature. This is a kind of optical sensor for temperature. So this is a very hot subject today, and this is called nanothermometry. So you can use particles to measure temperature, and these are nanoparticles, so you can have temperature measurements in the nanometric scale. So coming back to the work made by Karina, we have the upconversion nanoparticles, and we coat these upconversion nanoparticles with silica, porous silica, obtained by Sol-Gel. So we incorporate europium ions in the porous silica, and we fabricate in situ this complex of europium. It means that this particle, when you shine in the infrared at 980, upconversion nanoparticles will emit visible light in the green and the red. And when you shine in the UV, you will excite the europium complexes on the silica coating, and you see the red emission from that. So this is what we are calling dual mode thermometer, because the upconversion emission depends on the temperature, as I showed before, and the red emission of europium also depends on the temperature. When you increase the temperature, the intensity will decrease. So this is what we call a dual mode thermometer. These are some measurements for these materials. You have here the europium emission. When we increase the temperature, the intensity decreases. And here you have the upconversion emission giving temperature information too. So you have here the two plots obtained from the data of these two systems showing that you can measure the temperature by two different ways. If you increase the UV power, you will start to degrade this organic ligand that it's bonded to europium. And so what you observe in practice is the decrease of the europium emission intensity with the increase in the UV power. So this is also a UV sensor. So we can say that these nanoparticles are dual mode thermometers and also UV sensors. You can also play with silica particles and coat them with gold. In this case, we have a gold nanoshell. And we can decorate these silica particles coated with gold with our upconversion nanoparticles. Interesting properties are observed here, because when you shine in the infrared at 980, you will excite the plasma of these gold nanoshells. So you will heat locally the particle. When you heat it, you can measure the temperature by the emission of the upconversion nanoparticles. So what we have here is an optical nanoheater and together with a temperature nanosensor. These are some results. So you have here the absorption of these gold nanoshells, showing that the plasma is in the infrared region of the spectrum. So when you shine in the infrared, you observe the upconversion emission from the nanoparticles, and also you observe heating. So this is the temperature for the gold nanoshell samples. You observe the increase in the temperature with the power of the pumping laser. And when you don't have the gold, temperature is always the same. So we are showing here this nanoheating process, and we are measuring the temperature at the same time. We were talking about base catalyzed Sol-Gel materials. When you come to acid catalyzer, to give you some examples, so in this case, you have porosity at the nanometric scale. So we have transparent materials that can be used with different applications, as for example, transparent conducting oxides. So you have films presenting transparency and electronic conductivity simultaneously. You can also play with integrated optics. So you can prepare thin films, for example, erbium doped thin films, to have the amplifier, the optical amplifier at 1.5 microns. You can also play with the structure of the material in order to have a DFB laser. So you can have all these devices by playing with the sol gel process. What you see here is a thin film deposited in a glass slide, and this is the image you see here is from an equipment where we measure the guided modes of the samples. You have light coming from the right here, and it's coupled in the film deposit on the glass surface, and you see the green light being guided by the film. So sol gel is very rich. The main advantages of the sol gel processes are listed, some of them here. It's a liquid phase reaction, so you have homogeneity. You have mixtures at the molecular level. Versatility, you can prepare multi-component materials. Diversity of forms, you can prepare fibers, monolithic bulks, thin films. It's a low temperature processes. So you need light equipment, you have minimized production costs, and of course, you can incorporate organics. So the precursors are high periods, less and less expensive. So you can think about producing these materials in a commercial scale. So you can prepare, for example, compositions that otherwise would be difficult to be prepared. For example, silica titania, silica zirconia, the melting point of these mixtures is very high, and you can prepare them at almost room temperature. So there are some drawbacks, of course. So you will always have hydroxyl groups. After drying, a very fragile porous gel is obtained. Frequently, higher temperature heat treatments are needed to complete desiccation. And in this case, cracks will occur due to the contraction. Films are obtained for thickness up to 0.5 micron, not more than that. So thicker films can only be obtained by multi-layer deposits. And of course, there's a limited solubility for lanthanide ions. The solution proposed in the 8 is the addition of organics. So this is the work done by Helmut Schmidt in Saarbrücken in Germany. These are the so-called organic inorganic hybrids. Hormozyls from organically modified silanes. In the literature, these materials are also called hormocers or polycerams or nanomers, a lot of different names for them. And these materials are wonderful because you have both the good parts of the organic and inorganic works. So they are flexible, there is no cracking, they are processed like polymers. You can obtain thicker films, completely densified materials at low temperatures, and you can think about new functionalities. You can have, of course, tunable lasers by using dye molecules. Today, a lot of work is done on the so-called random laser, photochromic materials with inorganic or organic active species, hydrophobic organic groups, photodensified groups, organic precursors for semiconductors or metal nanoparticles, C60, and of course, high solubility for lanthanide ions. There are they play the different holes in the structure. So organics can these materials, this is the so-called Zachariasen glass network, and organic groups can play different holes in the structure. They can play the hole of formers, for example, leading to cross-leaking. They can play the hole of fixation of clusters. They can play the hole of adsorbents at the pores. A lot of different holes can be played by the organic parts. In general, they are divided into two types: The class 1, where you have polymer mixed with the inorganic material. So there are weak interactions between the organic and inorganic parts. And there are the class 2, where we have modified precursors. These are all liquid precursors that we can buy today. They are not expensive. And so what you see here is different functional groups attached to the silicon atom. So you have photopolymerizable precursors. You have here the epoxy group. You have here the vinyl group. You can have amino group. So this is a very rich chemistry that can be done today with no expensive precursors. Of course, this idea is not new, just to mention that the first organic-inorganic hybrid was made by the Maya. The Mayas in the Central America, they were able to prepare this blue pigment. And this blue pigment is made of an organic dye, indigo blue dye, and clays. So they were able to do that. And they still, you can still see their blue pigment after some centuries. So they are very resistant to weathering for more than 15 centuries. This is amazing. If you take this dye, it will degrade under the sun. And so they were able to prepare that, and must say that we still don't know exactly how they prepared their blue pigment, these first organic-inorganic hybrids. So we have here in the 80s, after the proposition of this kind of materials by Professor Schmidt, some papers became very famous with different applications. And but the common point that must be cited here is the mixture of components at the molecular level. There is no phase separation, so no light scattering, good optical property. However, we must say that in a nanoparticulate phase, the particles, solid state properties, are kept and lead to special materials. For example, the scratching resistances that we have in our glasses today, the control of refractive index, the local control of the refractive index, under, for example, particles can migrate, for example, under an electric field. These are the so-called green lenses. So all the very active area here is in the preparation of these building blocks for the organic-inorganic hybrids. So you have here, for example, the zirconium alkoxide modified by the metacrylic acid. So what you have is a oxo cluster of zirconium atoms modified by the metacrylic acid. In general, you have this kind of structure, a core, a metal core, and the functional groups attached to this core. This is a very nice chemistry, and you can have, for example, we can see this in a very famous inorganic chemistry book from '61. So this is the cluster that we have in aqueous solution of zirconium 4+. And this is the formula that we have for this species. The size of this colloidal particle is around 2 nanometers. This is the size of what we call today nanoparticle. In '61, this was not so interesting. And after that, I can mention the work of Professor Schubert in Austria. And these are some of the building blocks that he's able to prepare with tantalum, with hafnium, titanium, zirconium. This is a very beautiful work of Professor Schubert, very well known in the area. We did that some years ago. This is as an organic-inorganic hybrid that was cited last week by Ruth Ferreira, our colleague from Aveiro. And we used this hybrid together with our functional group in order to have materials that we could write optical waveguides and gratings with UV light. These are some results of that paper some years ago with the gratings and the increase in the zirconium nanoparticles content as we increase the zirconium content obtained by X-rays diffraction. And this is the last example that I'd like to show you is the organic-inorganic hybrid aerogel made of cellulose and molybdenum sulfide that we use it in water decontamination. So cellulose, we are talking about bacterial cellulose, a wonderful material produced by bacteria in the form of a hydrogel. Then when you dry, you can have a paper-like membrane like this. A lot of different applications is proposed. I must run with the time. So we can make bandages to treat wounds, to replace the skin. We can make tubes, we can make ophthalmic lenses. You can incorporate propolis or silver nanoparticles in order to add the properties of these materials. You can obtain transparent substrates in order to prepare transparent OLEDs. You can hydrolyze cellulose in order to have cellulose whiskers that will self-assembly in solution above a critical concentration in order to give you pneumatic chiral phases. So when you dry it, this is a thin film, and the blue color you see here is not due to a pigment. Is the color of the selected light reflection from the liquid crystalline structure. You can add photochromics, phosphotungistic acid. The membrane, when you shine it, it will change color to blue. Or if you can prepare aerogels and use the membranes so obtained in water decontamination. What we are doing is supercritical drying, CO2 supercritical drying. By doing that, you will obtain new aerogels and you can incorporate semiconductors that are used in photocatalysis. So we can do that with titanium oxide, bismuth vanadate, or molybdenum sulfide. So these are new materials where we have the good things of both worlds. The cellulose aerogels world with mechanical stability, flexibility, and macroporous, and the inorganic phase, the wonderful properties, the unique properties of these inorganic phases in photocatalysis and also in surface properties. So these new materials are suitable for practical environmental applications. So we did that. We used this membrane in order to decontaminate water, and the membrane was able to absorb organics, dyes, and also to remove heavy metals, for example, as chromium-6. When you shine, you will degrade the organics by the photocatalysis, and you will reduce the chromium-6 to chromium-3 in order to remove it from water. These are some more images of this work. This is the reactor with the membrane placed inside, and then you have a flux of the decontaminated water, and you shine the system with an optical fiber in order to have the elimination of organics and inorganics. So just to finish, this is some nano garden that we are trying to make here in Brazil. This is the cellulose membrane, the fibers you see, the nanometric 3D structure, that we can grow, for example, silica particles. This material is used for random lasers. And this is an image of a tree, a very popular fruit that we have here in Brazil, jabuticaba. So we are calling these membranes a nano jabuticaba tree. The molybdenum sulfide, if you see the structures that we have also attached to the cellulose fibers, resembles roses. So we are calling this nano roses structure. So we are building a nano garden here in Araraquara. Just to finish, I'd like to announce there is a International Sol-Gel Society, and this society organizes every 2 years the Sol-Gel Conference. So the next one will be held in Lyon, in France, from 24 to 29 July. And in the first day, we will organize there a workshop on the photonic classes by Soldier. So you are all invited to come to Lyon to attend the conference and the workshop. With this, I finished. Thank you very much. I hope I kept the time. Thank you. I think we can go. Stop share. Okay, thank you. I think you can go directly to Professor Rosolin, João-Batista Rosolin from the CPQD. Thank you, Rosolin, for accepting our invitation. You have the presentation.
Good afternoon. Thank you, Sidney. Let me share the screen. Can you see the screen?
Yes, but just put it in the presentation mode.
Okay.
Great.
Again, my name is João Rosolin. I'm from CPQD, and I'd like to, my name of my colleague Claudio Floridia, that are in the coordination of the Cisphoto Integration Laboratory. I'd like to thank to Funglass for this invitation, mainly to Professor Sidney from NESP. This is not a scientific presentation, but it's a presentation about the application and the interaction of many institutes in Brazil that research photonics. Some the outline of a presentation, some aspects of CPQD, and the labs in CPQD that works with photonics, optical sensing, integrated photonics, and optical communication. And then some aspects of the National System of Photonics Laboratories, known as Cisphoto, and the project using spatial glasses and fibers in Cisphoto. CPQD is a research and development center placed in Campinas, São Paulo. CPQD is 45 years old, have 970 employees, and have over 705 customers. The main technologies in CPQD at the moment are connectivity that encompass optical communication and wireless technologies, Internet of Things that encompass also software and sensing, and the sensing activities that encompass optical sensing sensors and others. Sorry, a moment. Okay, electromobility. We have a group that study batteries and their application and electrical mobility. Artificial intelligence as a group of software. Information security is a group of software, and blockchain also is a group of software. My research at the moment is in sensing system. Then I will discuss some aspects about. But just to understand, CPQD in the decade of 70 initiate the research and development of optical fibers in Brazil, and that time that it transferred the technology for some companies example of that time, that the research in that time, Francisco Smolka, that is the next presenter, was worked actively in this transfer of technology of fibers. In CPQD, I would like to comment about three laboratories that works with optics, with photonics. The first one is the laboratory that I work, LSMO. Only have a research and development of optical sensing systems for many applications during these last 20 years, mainly in electricity, in lines, transmission, substations, oil and gas, mainly with Petrobras and Repsol, and many transportation, like, for example, in Metro São Paulo, and the other sectors. In this photo, you can see some applications and equipment developed at our laboratory. And for example, the instrumentation of dance and the utilization of sensors in the medium voltage distribution network. The other laboratory is the Laboratory of Integrated Photonics, where we have integrated photonics technologies to carry out steps of fabrication, characterization, encapsulation, process optical devices. And the most laboratory is LASOR, that's a laboratory of optical communication that has electrical equipment and components to carry out high capacity optical transmission experiments in WDM, and many aggregate rates can be to more than 1 terabits per second in this setup. In March the last year, the Ministry of Science and Technology and Innovation in Brazil create the National System of Photonics Laboratories. In the name acronym is CISPHOTON. What's the objective of CISPHOTON is to promote innovation in Brazilian industry and on scientific, technological, economic, and social development. The CISPHOTON consists of a set of 10 general laboratories that are showing in the picture in this slide, and one integration laboratory. The 10 laboratories are distributed around the Brazil region, and mostly are in São Paulo state. And the general laboratories are multi-user with open access to the public and private users, and direct to research, development, and provision of technological service, entrepreneurship, and innovation in photonics. And to coordinate and integrate these laboratories, I'd like to comment before, some technologies that are researched in these laboratories. First, in Senai, in Santa Catarina, we have development of industrial lasers, and also in CENPEM, that is a Commission of Nuclear Energy in São Paulo, IPEM. Some problems on my presentation. Sorry. Sorry. And I have technology of agri-robotics using laser-induced breakdown. And that is a development of Embrapa in São Carlos. You have development in agriphotonics to the health of the plants and vegetables that are developed at the Universidade Federal Mato Grosso do Sul and University of São Paulo. We have development in phototherapy to cure some problems in skin that are developed in Universidade of São Paulo. We have special glasses and fibers developed in UNESP, as commented by Professor Marcelo Nalim. We have optical communication and system developed in CPQD, Universidade Federal de Espírito Santo, Universidade Federal de Recife, de Pernambuco, and Unicamp in Campinas. And we have development and optical sensing system in CPQD and Universidade Federal de Pernambuco, Unicamp, and Universidade Federal do Espírito Santo. And I have a mix of technology in these groups. CPQD, as I told you, has a special function in the Sysphoton because CPQD is an integration laboratory, and this function is to promote, to join the institutes using strategic intelligence articulation, the agendas between the general laboratories and the companies and the startups. In addition to dissemination, scientific technological innovation, and entrepreneurs activities carried out by the general laboratories. We are recently initiate a scale to interaction with the market and promote greater engagement of laboratories, industry, startups, and companies, and the laboratories of all sizes to enjoy the various applications of photonics in a unique and an open environment of innovation that we will call Sysphoton ecosystem, and are inviting startups, companies, and institutes to aggregate to our Sysphoton ecosystem. Sometimes my PowerPoint failure, then I have to ask you to give me a time. Sorry. Then I would like to show some interaction between some groups in the Sysphoton that works with special glasses and fibers. In this case, you comment about Unicamp, Universidade Federal of Pernambuco, UNESP, and CPQD. The first institute I would like to comment is about Unicamp that produce and research hollow core photonic crystal fibers. The current framework in research in photonics identified hollow core photonic crystal fibers is a new building blocks for the next development in the field of photonics. The LAF is the name of this laboratory of Unicamp. Research structured fibers using silica, soft glass, and polymer with innovative design for optical communication, device, and sensors. LAF designed fibers that are produced per LAF members in Campinas at Unicamp or at a partner institute, for example, in France. Sorry. The second institute, Universidade Federal de Pernambuco, that produce and research D-type optical fibers. The type of optical fiber is an optical fiber where the cladding is side polished, resulting in a D-shaped form. Optical fiber-based sensor with the shape are used to detect some phenomenon quantities such as reflective index, gas concentration, temperature, corrosion, biological substance, among others. In this case, the Photonet, that is the laboratory of Universidade Federal de Pernambuco, is developing research on corrosion sensors based on the type fibers. The next institute, NESP, as you previously assist on the talk of Professor Marcelo Nalim, research magnetic optical glasses and fiber glasses based on terbium containing borogermanate glass. Many types of research and tests are performed in there, thermal, structural, morphological, spectroscopy, and optical properties are investigated at UNESP and its partner institute in Canada, for example. UNESP and Unicamp are working together to test the glass and fiber as a current sensor that was shown by Professor Marcelo Nalim. UNESP and CPQD are working together to obtain an encapsulated current sensor with standard optical fibers using these glasses. And finally, I'd like to comment that CPQD are developing voltage and current sensors using special glasses. For example, using pocket effect for voltage sensor and Faraday effect for current measurement. The voltage sensors use a crystal of lithium niobate, and the current sensor uses a rare earth iron garnet rig, as shown here. They as the CPQD is an institute of follow for the application, we practically develop the concept of this sensor and contract a company in China to make the packaging. And the next step is to perform this packaging in CPQD. Here's some photos of this sensor to use direct in the medium voltage application. Here is the right is the photo of the sensor that are installed in the medium voltage distribution network. Then that is my presentation. Again, thank you very much for this invitation.
Thank you, Rosolém. So I think, I don't know if you have some questions to João. There's some questions. I don't know if we can do it now or we can do it later. We are just a little bit late, so I think we can move on and pass to Francisco Smoka to his presentation, and then at the end we can discuss about all the things that was discussed here. Please, Francisco, can you share your screen? You must turn on your microphone also. Microphone is turned off. Just unmute it on the left corner. We cannot hear you.
Okay.
Ah, great. Nice.
Okay. Okay. Thank you. Okay. First of all, it's a pleasure to share with you what we are doing here for the last 20 years or so. Okay. My name is Francisco Smoke. I'm working with fiber optics for a very long time, almost more than 40 years. And now we're still working with optical fiber, not by just in equipment, and we have a small company that we're still playing around with fiber. Okay. Our company was founded in 1998 by former people from CPQD. That's what Rosalém was telling us. And basically, after we developed the optical fiber and installed it, then we decided to go on to new adventures. Okay. In our company, we started activities where the manufacturing of optical fiber amplifiers. And this was the starting back in 98, and optical fiber splitters that we use on the optical amplifiers, okay? And basically, both technology were transferred from CPQD. That's it is. So that's a daughter company from CPQD, okay? And from 2004 on, we started identify going to other areas of technology, essentially because one reason was the Chinese people were selling those components very cheap, so we have to move on to new products to stay on business. Okay, so and we developed many products I will show you later on, and our basic support for research was FAPESP, is the State Research Support Foundation, and some CNPq also, federal government support also. Okay. Okay, we're basically doing work with all passive optical fiber components for various applications in optical networks. Okay, so optical fiber couplers, this was our first product. Optical attenuators, some of these products are based on the same technology, manufacturing technology that I will explain later on. Okay, special made components, and we were the only factory or making this type of components in Brazil. Nowadays, most of the stuff is still imported from China or anything. And optical fiber connectorization, specialized optical patch cords, just for custom-made industrial connector optical cables, and sale and service from products that we don't make, circulators, some special WDM and large core fibers, so on. Okay, so we have a list of products. Some of them we make, some of them we just buy from some other people and sell them around. Okay. Our basic technology from optical fiber couplers, and we use basic two equipment to make that. One is a graphite furnace, and the other one is the hydrogen flame fusing heat source. Okay, the basic principle of optical fiber couplers, that is the base of most of our products. Essentially, we have to fuse together two fibers. So we get the fiber, we strip the coating off, okay? Then we just put the two fibers together, and it just heat the sink for about 1,000 degrees or so, and we fuse them together. We fuse them together and we stretch it at the same time. So when we do this, the electric field in one fiber starts moving to the other one, so there's a coupler power between the two fibers, and this depends in what we couple to one fiber or to the other fiber depends on the the amount of stretching, the dimension of the fiber, and so forth. Okay, this is the basic coupling equation, a lot of mathematics, but anyway, when we start stretching the fiber, we can see light going fiber, then move to another one, go back to the first one, and so on. And this amount of light can go one fiber to the other one, depends on the wavelength of the fiber. So we have 2, 3 different parameters that we can play around to put light one fiber into the other one. Okay. So essentially, what we use that stuff, this is basically used for bidirectional copper, share light in, for example, bidirectional communication. We have a transmission in the receiver, the fiber, we can couple this light into one fiber, so we have bidirectional transmission of light between one fiber and the other one. Those characteristics has very small insertion loss, okay, and the bandwidth depends on the stretching and so forth. Here, as an example, we can make a double window we can transmit 4 wavelengths in both directions, okay, and then we have those WM coupler have the transmission curve, something similar to this here. So we have the transmission one window and transmission in another window here, so we can move fiber to another one. This is a one big technology that we can make those couplers, those WM couplers, using discrete components. But today there's another technology, a plane circuits that can make this thing just one chip only. Okay. And also we can make this other special custom device. One of them is one for Raman temperature sensor that then we can couple light from one fiber to the other, so we can take the light for the Raman temperature sensor using OTDR type of equipment, or we can make different type of structure here for different applications. This one they want for these 2 different wavelengths here, or we can make this equipment here. There's a quadplexer. We can use transmission and bidirectional transmission in one fiber and two different wavelengths back and forth. Okay, and also we can make a different type of components here, and one of them is as a fiber bending sensor that we can move this, put this in here, and this type of sensor is very sensitive to bending, of this plate, of this plastic plate here. Another product that we made after we get through with this optical components that going to move to another type of product that we can, because the other one we just imported. So we want to move on to electrical-based electronic components. We did a lot of different products for special products using our technology. One of them is just this type of thing here is a media converter for electrical utility company that use very high isolation here. Another different products for this was for a particular thesis on State University of São Paulo, was for the solid state optical amplifiers type of module, multiple sources with different wavelengths here for application, urban fiber amplifiers, white light source. So there's a bunch of different products that we're making here, all using fiber. So everything that we make has fibers in and out, one way or the other. Okay. Using this here, one product that we did a couple years ago is a Huawei CalBox systems. I don't know, on the street have the different telephone booth separate by 1 kilometer from each other, and they use fiber for transmission and stuff. It's a very structure very similar to the fiber to the home type of application. So, but they have this, totally have a very low power consumption, use a small solar panel. And so we made the, we installed this system in different highways in Brazil here. And so we made the determination, the head end, the operational software, and so forth. So it's very similar to the FTH system, but different as a 2 wavelengths, just one single fiber, and we can communicate. A person just press the button here, opens the call, the software identify from what point the person is calling, then we can attend and send ambulance or some other kind of service that they need. Okay. Now we have another type of products that we call R&D products. They essentially play around with fiber as a sensor. And one of them is this product here is a landmass sliding detector. When you have rains, a lot of rain like we're having now in the state of Pernambuco, when there's a lot of rain, the part of the earth can fly down and go down the top and go on top of the house and stuff like this. So we're developing a product that is essentially long bars here, about a few meters long. This is a test one that they will stretch this thing that you put on the ground, and when the land start moving on, it just deflects this bar for it's very, very small, and there's inside this bending sensors here, and then we can detect the bending and send alarms when the land starts moving down here. Okay, and all those bending sensors is all fiber. I mean, there's no electronics, nothing like that. Just only connection here between the central and the detectors, also the optical tie-in reflectometers, the equipment that's used very often in optical networks. So with the fiber detects here, we can detect the movement of this thing. It's a kind of destructive sensor because one is bending, then you have to move on and put another one, but it's something that you can put in a mount in different position here, and just as the fiber, a very low profile here, there's no something that is very easy to put on the ground here, so nobody can mess around with that. Okay, so these are a product with just tested here and different applications. This was a capacitive type of product that we developed here. This is one of family of sensors. This is the bar that goes inside here. The sensor is mounted inside this bar here. Okay. And another product that we made years ago was optical fiber vibrometer. Again, is a seismometry or something, frequency detector, mechanical frequency detector, all passive. There's no electronics, nothing like that. It's a thing that's just the fibers, the sensor sits here. There's a spring here. And when this thing moves on, this thing starts moving around, then the sensor detects this movement and sends to the fiber. So something that you put the fiber, and you can put this distance between about almost 10 kilometers from the basic optical unit. So we can, the sensors are all optical, there's no electronics, nothing, no electric parts here, okay? It's basically for low frequencies up to 20 hertz only. So basic stuff and small masses, and this thing weighs a few kilograms only. Okay, there's also we call a software that you can monitor the thing here in the texting. One example here, for example, this detector put on the bridge This detector station on the bridge. This is the movement of car passing through the bridges. You can detect it optically from 10 kilometers only distance of car moving on bridges, for example. Okay. So basically, these are the products that we make basically all based on this type of optical fiber coupler, and you can use a transmission or kind of sensor, lots of applications using this type of product. Okay. Well, I think this is what I have to tell you, and also we have some other application in training optical fiber technology, components, and so forth. And also we do some work on fiber to the home design of systems and consulting on optical technology. So basically, we are a very small company, on a few people only, and we are surviving day by day, month by month, on the list. Okay, and so this is the basic contact of us. Ildefonso is the main shareholder of the company. He's also a CPQD person that used to work there on the laser development many years ago, and myself. Okay, we are located in Campinas, very close to CPQD, and so I don't know if you have any questions. I'm ready to answer them. It's something very different from what we're hearing about as very sophisticated glass technology. We are very down to ground system. This is how I have to talk. So I got 12 o'clock, so this is the right time to close the presentation. Thank you.
Thank you, Francisco. And I would like to thank you, all of you that stay up to now. And now we have some time to discuss this all these presentations. So if